Today we're going to discuss conformers, conformational isomers sometimes they're called, but a conformer is a different arrangement in space resulting from rotation of a bond. And we have kind of covered this, right? And when we discussed that sigma bonds can rotate and you have different conformations of ethane, like the Eclipsed and the Staggered conformation. And so I've made this little GIF down here. And it's an animation that takes you through there's ethane there. And this is a program that tries to constantly minimize the energy of ethane. And you can see I've rotated it. Now it's in the staggered conformation. That's sort of what it looks like, and rotated and still in a staggered conformation, right? And so it's always going to want to be in that staggered conformation. I can try to wrestle with these hydrogens to put them into the eclipsed conformation where everything is overlapping, but it will always try to relax back. Now there's important implications in this particular model. So the relaxing back, the desire to be in the staggered conformation, is related to something called Sterics, and you can see as I add another substituent there that the desire for it to sort of remain in the staggered conformation, where this methyl group right there is sort of looking across through the hydrogens there, right, is going to be greater. And now that I've added two, these definitely don't want to be eclipsed with each other. And the reason that is because of something called Sterics, right? And so Sterics, and you can see I've got it here. Oh, look, see, it's relaxing back. So Sterics, crowding. All right, so let's just say Sterics are equal to crowding. And you can see in this little animation, maybe not in this angle, but as it rotates around, that the hydrogens in some of these places, if you just bump them into each other, they get super close. See this? Super close to each other. And that is not optimal. So I can kind of rotate this around, and I can show you that just the fact that, so this molecule, all this is butane, right? All that is this compound. And they're already practically smashing into each other. So Sterics plays an important part in these conformational equilibria and these conformational positions. And I think it's a good idea to sort of get an idea of how we can both depict and discuss these. So if we look at, let's go back and consider just ethane, okay? So if we just consider ethane, I'm going to get rid of this here. If we consider ethane, we think about ethane and how we normally draw it. We normally have something like that, and there's a hydrogen and a hydrogen, and draw dashes and wedges, all right? And I'm going to make one of these hydrogens red, so it's very clear, so we'll be able to keep track of it. And a hydrogen here, and a here, and a here. And you'll remember that there's, if I just do a 60-degree rotation about this bond, mere 60 degrees, I end up with a conformation that now looks like this. All right? So I have rotated the bond, and I've kept the one and back conformationally the same, but I'm just sort of focusing on rotating the front methylene group, sort of, if you will. And now, and this is an important thing to keep in mind, a 60-degree rotation about this bond here means that this hydrogen is now going to be this hydrogen, all right? Because it's rotated in this direction right here, so that's going to come a little forward. And then this hydrogen is now going to be popping out over here. So that would be this hydrogen right here. It's now this one. And then you have this hydrogen. Let's pick a different color, green. And black definitely won't work. Let's go with pink. This hydrogen right here is now going to be the hydrogen going back here, right? And so now we can see that this hydrogen and this hydrogen are running into each other. And just like in my GIF, you noticed I actually didn't look at it side on. Looking at it side on is a little bit less instructive. What we can do actually is look at it down the bond, and we can depict that using our eyeball of science. Okay, so the eyeball of science looks like this, and it peers down that direction. So this is our visual cue, our visual indicator, and you can even draw some lashes on it, and like a big Cheshire grin, if you will. But that's the idea, is you have this eyeball of science that can look down and look at the difference between these different conformations. These conformations that I have previously called staggered and eclipsed. All right, so the staggered and the eclipsed conformation. And what those look like is, if we look down, let's look down this one first, okay? We're going to look down the staggered conformation first. And we're going to keep track of this red hydrogen here. All right, and if we look down that conformation, what we see is we first draw sort of like this little peace sign propeller doohickey. That's the carbon, that's the atom in front, okay? And then for the ones in the back, to really make it clear there in the back, we sort of draw like there's a circle, but the circle, of course, is behind everything. And I can actually keep track of the atoms here by keeping my colors. So if I go with this, I don't know, is that fuchsia, pink? I'm not sure. That goes there. And then this green one, that goes there. And then this blue one goes there. Okay? Oops. Now, I can redoodle my 60-degree rotation, okay, into the formation of the eclipsed product. And I didn't rotate my, well, here's what I've done. I've got to move my eyeball of science in order to stay consistent. All right, I'm going to move my eyeball of science this way. Boop, boop, boop. All right, that way. Now I'm looking down the same carbon as I did before. All right, eyeball of science and down there. Again with the propeller, hydrogen, hydrogen, hydrogen. Oop. Let's go back to white. And then the back carbon. All right, and then the back carbon, actually what we see is that red overlaps with the pink. And this white overlaps with the green. And then we can actually use this. This white overlaps with the blue, right? So now I can go back and get my blue, and then I've got my blue down here. So now I have this convenient, actually it's got a name, projection called the Newman Projection. And the Newman Projection actually does a pretty decent job at helping keep track of this rotation. Now you saw in the GIF that I produced that this staggered conformation was always, that's an energy minimizing program that tries to put things into the lowest conformational isomer it can. And it kept forcing itself in the staggered position, which of course implies that this eclipse position is higher in energy. And as you can imagine, you can keep doing this 60-degree rotation ad nauseum. So this pink hydrogen can keep rotating around the back and around and around and around forever, right? But every time it has to go, every time it does a rotation, it's going to go over some sort of bump, some energetic bump. And the energy landscape of this rotation, as you start out at some point, we can draw it here, right? And we can start at some relative energy where the lowest conformation is the staggered conformation, and then the highest conformation is the eclipsed conformation. And then that sort of will repeat itself, right? And so if we start down here at the staggered conformation, which we've agreed is this, that right there. And we go down to the Eclipsed conformation. Which will be up here. Then we go down one more because we do another 60-degree rotation, right? And that 60-degree rotation is going to move that pink bond that way. And what that would look like is we remove that. And we now look at what another rotation of that will do if we, like I said, keep moving it this way, is it would put the pink here. The blue now would go over here, and then the green would go up, okay? And you can see as you keep rotating it around, you keep getting this oscillation between the eclipsed conformation and the staggered. Now, once you have that, then essentially starting to replace these multicolored atoms will give you different energies, right? So we can actually say with some degree of certainty and highly predictable that the energetic difference at this trough, and it's not a great peak, is it? And that peak, the energetic difference here is 3.0 kcals per mole, all right? And that energy is totally surmountable at room temperature. You have enough thermal energy in the surrounding environment to allow this rotation to occur rapidly, and with basically it's constantly rotating. It's an easy barrier to overcome. Now, what happens, of course, when, say, you replace one of these hydrogens with a methyl group? So, in that particular case, the energy landscape doesn't change, because what you still have, in fact, we can just wholesale copy and paste that down here. What you still have is a single eclipsing event. So if I were to take the magenta one and pop it off and off and off, you would see, and replace the magenta one, oh, let's do a different color. Really drive home. What have I not done? Orange. Ooh. With a CH3 group here. All right, so now we've got propane, right? So up here is ethane, and now this is propane. And this rotation, it still undergoes an eclipse conformation. It still goes a staggered conformation. You can see it's basically going to do the same thing. This time, though, it's not 3 kilocalories per mole, but because methane is larger, it is now 3.4 kilocalories per mole. So that larger steric encumbrance has now made this rotation about the bond, the sigma bond, harder, okay? Just slightly. Now, things become a little bit more interesting, right, with larger systems. So a larger system like butane now has a much more complicated energy. It's not much more complicated. It's slightly more complicated. A slightly more complicated energy landscape than before. So you can see, we still have some eclipsing. We can do still some staggering, but there's varying levels of energy, right? So the way I've drawn it here, I've drawn what you typically see. You draw the methyl groups the furthest apart, and that is actually a low energy conformation. In fact, that's the lowest energy conformation that you can draw, right? Is if you have in your, we'll take our eyeball of science and in some sense, it actually doesn't really matter which side we look down, does it? When we look down that side, what we see is a CH3, all right? And you know what, let's keep the CH3, let's keep that orange, all right? And we'll keep the hydrogens white. All right, and then looking down the back, you have that CH3 and those two hydrogens here, and those are actually completely separated. So they're staggered, but in this particular conformation, they're actually anti. They're anti to each other. Okay, so they're completely opposite, right? So if I do a rotation about this of 120 degrees, so two 60-degree turns, right? So it's going to go through some sort of eclipse conformation, then it's going to go into another conformation. We would end up with something that is going to be a little bit more congested and a little bit higher in energy. So if I take this, I erase this, right? So I'm going to do 120 degree, and I'm going to put the CH3 here. I'm going to put the H here now, okay? So now this is actually slightly higher in energy than this, okay? Than this. And that's slightly higher. It's just slightly more awkward, if you will, than the anti-configuration. And so we call that a gauche configuration. The gauche configuration being just slightly more higher energy than the anti-configuration. Okay, and you can do, of course, another 120-degree rotation over here, and that would give you the other gauche conformation. Okay, and just like there's two lower energy systems, right? So these are two sort of like, these are the lower energy systems. There are also two higher energy systems, right? Where you can imagine the conformation where this is rotated just by 60 degrees. So basically where that started. So where we started from. So what are we? Let's actually, so we're going to rotate this way. And if we do that, what we end up with is a CH3 and we then look at the back CH3, and that back CH3 is also essentially eclipsing the front CH3. And so this is the highest energy configuration you can pretty much imagine. Okay, and so what we would call this is essentially a totally eclipsed configuration. All right, and I suppose that's probably an official name, but totally eclipsed. All right, so this is the highest energy configuration one can have. And then it rotates 60 degrees this way, and then you get this. And then you can have another eclipse conformation with another 60-degree rotation, right? And so that configuration looks where that is now situated, the front CH3 now situated there, and you got something here and you got something here. Now this is still eclipsed. Let's just call it eclipsed. It's higher in configuration, it's higher in energy than either of these two, right? And higher in energy than these two, and it's lower in energy than that one. So if we were to draw an energy landscape now, zoom out a bit, we go back here, we can draw our energy landscape, delta E. And so we have some high energy configuration, and that would be your totally eclipsed. And then it goes through this first gauche configuration, right? And so that would be this one. And then it goes to the next eclipsed configuration, which is not as high energy as the initial starting totally eclipsed, but still higher in energy than the gauche. And it goes all the way down to this anti-configuration, which is now the lowest in energy. Okay, and you can see that this still varies periodically. And of course it's symmetric because you can keep going around and around this circle. But this is essentially what you end up with, right? You end up with a slightly, I wouldn't even say it's particularly more complicated, but a slightly more complicated energy landscape. And I can just move these down here to really see if I can get them into the positions where they belong. So that's the totally eclipsed. I put the gauche in the wrong place. That was gauche of me, right? Gauche in the wrong place. And then that eclipsed configuration, that can go right there. And then you can keep rotating yourself around this energy landscape like that. And that is what you would get when you have the sort of substitution pattern. And that's a pretty good representative example of, and you can build on this, of course, with additional substituents. Now, the energetics of this, if you want to know, what we would say is, we'd set our absolute relative minimum is going to be this anti-eclipsed. And so the first gauche level from here down to here, that's actually got a higher configuration. Okay, so that's about 16 kilojoules per mole. All right, and then the difference, I've actually probably made it a little bit too pronounced here, but it's okay. Only trust numbers. That difference between here and here, so we look at this difference from here to here, that difference is 3.8 kilojoules per mole right here, okay? And now the totally eclipsed, because remember this is the totally eclipsed also over here, totally eclipsed conformation, and its energetic difference from the totally anti, or just the anti, so it's a bit redundant, is 19 kilojoules per mole. All right, so there's a much bigger difference in the anti configuration at 19 kilojoules per mole than 3 or 3.4. But you can see actually even just the gauche configuration is higher in energy than the eclipsed configuration is in the propane example.